Welcome back. So we're finishing chapter 13 with the discussion of volume. So this is section 13.4, talking about volume. And so volume is a measurement on, again, on a three-dimensional space, but it tells you how much space that the three-dimensional figure occupies. So your measurement will also be like a three-dimensional measurement. We talked about this uh, in a little bit when we were talking about units of measurement for volume. But one way of visualizing what we mean when we're measuring volume is by thinking of taking like a box and filling it with unit cubes. So as an example, from this figure in your book, we can imagine that each of one of these little blocks is a 1 unit by 1 unit cube. And then you could judge the volume of the larger box by seeing how many blocks fit into your cube. And so you can see that four blocks fit along the bottom. So like 4 by 2 row fits along the bottom, and we can stack them 3 units high. And using this method, we could directly count how many blocks are in this box. But of course, just by, again, like this being like a model for multiplication, this is what tells us that our volume measurement is just going to be the length times the width times the height. So if we were to count this up, there would be in this bottom, like in the base here of this box, there would be 4 times 2 rectangles, which is 8. And then we would make 3 different, we would stack that up 3 times. So that would be multiplied by 3. And so in this case, we get 8 times 3, which is 24 units cubed in that example. Of course, in the example of just looking at a cube instead of a rectangular box, here we have the side lengths are all the same. And so when I take the volume of a cube, I'm just multiplying the side lengths up. And so that would be s cubed. Okay, in that specific case. Okay, so more generally, we talked about prisms when we were talking about surface area. And so we started with this idea of what happens with a box. And we kind of disassembled this box when we were thinking about surface area. When we think about volume, we want to generalize the idea for filling this rectangular box with for a prism. And I think to rigorously derive this, again, I think most of these formulas would, the way that I can think to do them would involve calculus, which seems unnecessary, but we can talk about kind of where one motivation for where these come from, at very least. So for a general prism, so again, we have 2 of these little, in this case, we have, what is this, a 6-sided figure, a sexagon, I think. This is, so A is going to represent the area of that 6-sided figure. And so my volume is going to be the area of that figure. And what we kind of want to imagine doing here for kind of motivating these formulas is I'm going to take that area and I'm going to multiply it by the entire height. So we can kind of think of like what we're doing is we're like stacking up a bunch of these little areas. Infinitely many times is really what we're doing. And that's sort of akin to what we were doing in this rectangular box case is we took the area of this base and we stacked it up, in this case, 3 times because that was the height. Now we're going to stack it up h times because that is the height of our prism. So it's the same idea. Okay, so let's look at an example computing this. Of course, okay, so here we have the volume. We want to find the volume of a right triangular prism whose height is 4 and base of the right, and the base is a right triangle with legs of length 5 and 12. So when we talk about the legs of a right triangle, we're usually talking about the ones that are not the hypotenuse, the sides that are not the hypotenuse of a right triangle. So I've kind of drawn, or I have drawn this picture. It's not the best picture you've ever seen, but it works. So this is my little piece of cheese prism, and we have, I made that worse. Okay, sorry about that. So this is like my right triangle here, right? And so this is side length 5 and this is side length 12 on my prism. And so I want to find the area of this top section, right? And multiply it by the height, which is 4. So to get the area, I want to find the area of this triangle, which has a base of 5 and a height of 12 for that triangle. And so this should be 5 times 6, which is 30. And then for the volume, and so notice the area of that triangle, are we given units here? I don't think we're given units here, but this would be units squared, right? Because that's an area. And for the volume, we're going to then multiply that number by the height. So it's going to be 30 times the height, which is 4. And that is 120. And since this is a volume, so we're multiplying 30 units squared times 4 units, so we should end up with units cubed. In general, if there's no units assigned, I'm not going to be too picky about needing to state, generic units, but I think it is a good thing to get in the practice of. 1, just so you don't forget to mention units, and 2, just so you can kind of think about what the dimensions of the units should be, whether it should be units squared or units cubed. Okay, so now let's look at a couple other shapes here. So looking at the cylinder, we're going to kind of use a similar form, and the volume of the cylinder is just going to be the area of this top circle times the height. But of course, in this particular case, we know what the area of a circle is, and that's just depending on the radius. So for the area of this circle, we're just going to use this radius r, and so that should be pi r squared times the height, and that should give me the volume of a cylinder. So one thing to kind of keep in mind here that maybe I should have brought in when we were talking about surface area is to kind of notice that here we have we're multiplying. We have two radius lengths, right? We have r squared and another height length to get a 3-dimensional measurement. So this is kind of a good reality check if you're kind of wondering, do I have the right formula, or do I have the right number of parameters, or are my units correct? Here we're talking about a 3-dimensional measurement of volume, and so we should have 3 length measures that play into that formula that are being multiplied. Whereas if we look at a surface area, we should only have 2 that are measurements that are multiplied. So if you can see, like if we compare the surface area of a cylinder. Sure, I have r times r, so that's r squared, and r times h. And that's but we're just adding to two-dimensional measurements. So that's a two-dimensional measurement, as opposed to multiplying three of them. So hopefully that makes sense a little bit, but these dimension checks are really helpful ways to kind of check your understanding as you're going through and constructing a formula for area or volume to make sure you have the right amount of length parameters in there. Okay, so that's for our cylinder here, and I'll move this up a little bit. For pyramid, we want to use a similar, our formula we would expect to be similar, except the problem is, the problem that's happening here is this area is not remaining uniform among through the whole height, right? So here for the cylinder it is, right? I'm just kind of taking infinitely many copies of this circle all the way down. But for the pyramid, I'm not, right? I start with this little sexagon, and as I go up, it's getting smaller and smaller, right? It's not remaining uniform. So again, we're going to want this formula in terms of the height and the area of this little bottom geometric figure, which in this case is a six-sided figure, but could be any amount of sides. So we would expect, like before, if I had the area times h, well, that would have given me the volume of the prism, right, that had both a top and a bottom that were the six-sided figure. Here, what happens is we actually need to multiply that volume by a third, and the basic idea is we have a third as much volume as we did in the prism. So your book has this figure that attempts to sort of show you how we know we have a third of the amount of volume. I stared at it for a little bit and don't know, it finally made sense to me, but this is not a proof, and so it's not super rigorous, so I don't know how much it will help illuminate things for you. But the basic idea is I start off with this box, which is a prism, and I know what the volume of a prism is. And what I'm going to do is I'm going to take this prism and I'm going to break it into three different pyramids. Okay, so basically I take this corner, which they labeled V here, this vertex, and I'm going to make that like the pointy part of all three of these prisms. So one of them I'm going to take and have that be the top pointy part of the prism, the pyramid, and then this is going to be the base of the pyramid. And so that you can see that they have labeled that one with this the base is labeled in orange. The other one, or one of the other ones, is going to go from that vertex and make the base of their pyramid the bottom part here, which they've labeled in blue with the number 3, right? So notice that these two pyramids that we have so far, they don't overlap, right? And then the third pyramid again starts at the same vertex with the top, and then the base of that pyramid is the back of my box here, which they've labeled with 2 in yellow. And so you can kind of see this better now. They've pulled them apart, and this is what they look like pulled apart. And I think the basic idea is, this is not shown, I don't believe, maybe your book does show it, but the basic idea is that in this one box, we can fit 3 different pyramids, and so and that would fill up the whole volume of the box. So the volume of each of these pyramids should be 1/3 times the volume of the box, which is what we have here. So that's the basic idea. Great. Okay, so let's do an example of this because this is one that I think can be a little bit complicated to compute. So it is good here to think about and to be careful about what we mean by the height. So oftentimes when we were talking about the surface area, we were just taking some length of a side here, but that's not the height. And the height is actually what happens if I go, oops, undo that. If I go vertically up um, perpendicular to the base all the way up to the point. So the height is perpendicular to the base and kind of like imagine lives inside. So this can be an often a harder unit to measure. So for this example, if we want here to find the volume of this pyramid, what they're giving us as 17 is not actually the height of this pyramid, it is the length of this side, which you could probably easily measure if you had some sort of solid pyramid, okay? Um, but measuring the height on the inside might be a little bit more difficult. And so we have to use a little bit of geometry in order to do that. So one thing we need to do is we need to get the area of the base. So let's start there, and then I'll come back to finding this height. So let's find the area of this base. So it's a six-sided figure. So let's draw this out. And I think, oops, okay, let's see. It won't be perfect, but it will be decent. Okay, so here's my base. I know this, each of the side lengths is 8, is what this is telling me. And what I want is the area of this thing. And so just like we did with that like octagon when we were finding the area of a circle, what we want to do is we want to break this up into a bunch of little triangles. Okay. Okay, and if I do that, I actually have that the sides of each of these triangles, they're going to end up being equilateral triangles, each of length 8 here. So this allows me to find the height of the triangle using the Pythagorean theorem. So now let's look at this triangle. So this height of this triangle, maybe I'll call this, well, I called it H, or no, I called it A, that's what I called it. So this is A, and this is, of course, this piece is length 4, since the whole side is length 8, and this guy should be length 8, and I get A squared, sorry, plus 4 squared is equal to 8 squared. Doing a little bit of arithmetic, so 4 squared is 16, 8 squared is 64, subtracting that over, I should get that A is the square root of 48, or 4 square roots of 3. And so now I'm able to find the area of this triangle. So area of the triangle is equal to 1/2 the base, which is length 8, times the height, which is 4 square roots of 3. And so that's 16 square roots of 3. Okay, and so I found the area of that triangle. So to get the area of the whole six-sided figure, which is this little figure, this is going to be 6 times that total area, which is 96 times the square root of 3. Okay, so last but not least, to find the total volume, we need to multiply by the height of this figure. So it means I need to find this height, h. And so I have another little triangle that's kind of, we can imagine like embedded into this pyramid. And this is not really to scale at the moment, but it looks something like this pink triangle. This side length we said was 8. this one is 17, and then this is my right angle. And so this is this height of the pyramid. And so again, using the Pythagorean theorem, we get h squared plus 8 squared is equal to 17 squared. And again, just squaring these values and solving for h, we get the square root of 225. So that should be 15. So putting this all together into my volume formula, the whole volume is going to be 1/3 the area, which was 96 times the square root of 3, times the height, which was just 15. And altogether, I think this is 480 times the cube root of 3. And my units, again, should be cubed because this is a volume, which is a 3-dimensional measurement. Okay, so it's okay. You can just leave, since the square root of 3 is irrational, you can leave it in this form if you would like for your answer, as opposed to trying to get a decimal approximation. Okay, so finishing off with the last two volume formulas that we're going to use. So if we're talking about the volume of a cone, so the shape of a cone we can see is like very similar to the shape of a pyramid. So we would expect that these volume formulas should be roughly the same. And in essence, they really are. So the volume of a cone is going to be 1/3 the area of this base region and times the height of the cone, where the height is that vertical height straight up, not measured along the side. But in this specific case, we know exactly what the formula for the area of this base region will be because we know the area of the circle, right? So again, we're just going to use that here. So this is going to be 1/3. The area of that base is the area of a circle, which is just pi r squared. Sorry. Pi r squared, and then times the height. So this is our formula for the volume of a cone, where that base has a radius of r. Okay, last but not least, looking at the surface, or sorry, the volume for a sphere, we can again use this what do I want to call this? This like relationship, I guess, that Archimedes found, that the volume of a sphere is 2/3 the volume of a cylinder. And so what we need is just the radius of our sphere. And then we can use the volume formula of the cylinder, and it should be just 2/3 of that. So the volume of so in general, sorry, I guess sorry, in general, the volume of a cylinder, remember, was pi r squared h, where h was the height of the cylinder. But again, we have this picture where the cylinder that we're talking about is the one that has the sphere kind of perfectly embedded in it. So actually, let me do this. Let me put it in blue, and maybe that will make it clearer. So the cylinder that we're talking about is, well, this is not perfect, but we can kind of see it matches up perfectly to fit the sphere. My picture is not exactly perfect, but hopefully you get the idea that the point for the cylinder is that specifically we know what the height of the cylinder is. So the radius of the these base circles is going to be the same as the radius of our sphere. You can kind of see from the picture. And so the formula for the volume of the cylinder is going to be pi r squared h. And then the height is going to be just 2r. So that means pi r squared times 2r. So that's 2 pi r cubed. So that's the volume of this blue cylinder. And so since the volume of the sphere that's embedded in it is 2/3 the size, it's going to be 2/3 times 2 times pi r cubed. So that's 4/3 times pi r cubed is the volume for the sphere. Oops. Okay, great. So that's where this volume formula comes from. Wanted to finish off doing one example and point to a couple other resources to finish off here. So just like our last example in the surface area case, I want to look at an example where we kind of put together a few different figures. So here we have an ice cream cone with a slant height of 13 centimeters. It seems large to me, but maybe it's not. I don't really. I'm not sure. I don't have a ruler on me or an ice cream cone, unfortunately, so I can't tell you how large that actually is. But so when they're talking about the slant height, what they're talking about is this length here along this part of the cone, not like the height of the cone that's perpendicular from the circle piece. Okay, so that's the slant height, and it has a diameter of 10 centimeters. So that means just the radius up here should be 5. Okay, so if the cone is filled with ice cream and there is a perfect hemisphere or a half sphere of ice cream on top, how many liters of ice cream are used? So there's quite a few things going on with this question, which is why I liked it. It also involves ice cream, so there's nothing bad about this question at all. Okay, so except for that the fact there is no real ice cream, and I can't get some since I'm in quarantine. This is so sad. Okay, so this is the thing that I want to find the volume of, kind of imagining this piece of ice cream goes like this. That's not bad. Okay, so first things first, let's find the volume of the cone. And we are given the slant height and the diameter of this base, but we'll want, of course, the radius, which should not be bad, right? So the radius we said is going to be 5. And of course, we will also want the like actual height, not the slant height. So let's look at this pink triangle that this constructs here. So we have this slant height of 13, and we have this short leg of length 5. And of course, the Pythagorean theorem tells me that the height then should be h squared plus 5 squared is equal to 13 squared. And so if I solve for h, so this should be h squared plus 25 squared, or sorry, plus 25 is 13 squared, and 13 squared is 169, that's right. Okay, 169. So I'll take that 169 minus 25 and take the square root. What I should get is 12. So 169 minus 25 should be 144, and the square root of that is 12. So this height is 12. So this should give me the volume of the cone. Or help me get the volume of the cone. So that will be, oops, I think I wrote this wrong. Okay, so 1/3, and then the area of this circle, so that's pi r squared, which is 25, so pi times 5 squared times the height, which is 12. Okay, and so simplifying this, I think we should get 100 pi centimeters cubed when I put my units in, because these units were centimeters, and we are talking about a three-dimensional measurement of volume. Okay, so that's the volume of the cone. The volume of the scoop, or hemisphere as they were calling it, is, oh, that's the purple piece, right? So, well, it's going to be the volume of the sphere of radius 5, but divided by 2. So that's going to be 1/2 times the volume of the sphere, which is 4/3 pi times 5 squared, or 5 cubed, I'm sorry. So this inner piece is just the volume of the entire sphere, and then we are going to divide by 2 to just get that half top piece, because we've already accounted for the piece of the ice cream sphere that is inside the cone. Okay, so that is, and I think if I simplify this, I should get 250 over 3 times pi centimeters cubed. Okay, so now let's look at this total volume. So the total volume is, of course, adding these two things together. So that's 100 pi centimeters cubed plus 250 over 3 pi centimeters cubed. And that is approximately 576 centimeters cubed. And centimeters cubed is really what, in terms of liters, is what a milliliter is, right? Because yeah, I think it was a decimeter cubed was a liter, so a centimeter cubed should be a milliliter. And so turning this into liters, then that's 0.576 liters. So this is just using those conversions from section 13.1. Okay, so to finish off this section, I just wanted to point you to the fact that at the end of this section on page 703, they have all the shapes listed out. I wish there were pictures here. I feel like that would be nice and a little bit more helpful, especially with the notation embedded, but I'm sure you can fill those in based on what we went through. And the different formulas for both the surface area and the volume for each of these. So there's a nice little table that they do give you at the end. And I encourage you to draw a little picture so you know which each of these parameters corresponds to with the different shapes. So I have a couple different questions here listed out that you might want to talk through with me or think about. The first one I thought was kind of fun. So we have a rectangular piece of paper that is rolled into a cylinder in two different directions. And we're assuming that we don't like overlap the edges to like glue them together or whatever. They're just touching. There's no overlapping. Which cylinder has a greater volume? The one with the side length of the rectangle as a height, or the one with the short side length with the rectangle as its height? Or is the volume the same? So I like that question. I think there's a lot of ways you can try to answer this question, which I think is good. And then again, a couple things talking about questions asking about dimension. I think with 32 and 33. Oh yeah, 33 is looking at the volume of a pyramid and and asking about the slant height versus kind of the the like actual height of the pyramid, if the slant height is necessary. Okay, so there's that, and great. A couple other questions involving these volume ones, 37 and 38 at the end of the section. All right, well, that summarizes the content for the course. So thanks for joining me, and I'll see you soon.